Hello guys, welcome back to my channel Gamma Die Gamma. So I expect or at least hope that you guys watched the last two videos on the Taylor and Laurent series. I am going to talk a little about singularities and the classification of singularities. And if I have time, maybe even talk about residues in this video, and then we can move on to way more interesting things. So let's get started. Before I talk about anything at all, I would like to clarify one thing. I've been using singularities and poles interchangeably, but there is a fine difference between them. A difference I will be talking about in this video. So let's first define what singularities are in a less rigorous way. Say if you have z is equal to a point on the complex plane, if that is a singularity, of the function f of z, and what I mean by a singularity is that if you take the limit z goes to a, f of z, well, f of z is going to diverge to positive or negative infinity, or it can keep oscillating if it's like a trigonometric, circular trigonometric function. Okay, this is, I don't know, a really informal definition of a singularity. I think that works. So you can think about this as like a danger point. Think of it in terms of real functions. When you have 1 over z, the limit as z goes to 0 will give you positive or negative infinity depending on what side you're choosing to take the limit from. Okay, this is one important idea, or this is one clarification I would like to give. The other is, let's talk about poles now. So if the most negative term in the Laurent series expansion of f of z, some function around the singularity point z equals a, has power negative m, then the singularity point is called a pole of order m. Okay, let me give you some examples of this. This is too much theory. Okay, so assume that you have f of z is equal to 1 over z minus a. Again, if you kind of plug a in or take the limit at a, you'll see that z equals a is a singularity point. I mean, this shouldn't be surprising. Well, what if we try to write basically the Laurent series expansion of this guy about z is equal to a? So I'm going to write a general form of our expansion. These are the negative terms, and then these are the positive terms from 0 to infinity. Okay, we need to basically find the orders. For that, we need to find the coefficients and actually see which ones are going to be there in this expansion. One way of thinking about this is like try to compare powers, as it's kind of like a polynomial. It's not exactly a polynomial because there's like these negative powers, but What we can do is we can try to find these coefficients if comparing coefficients does not seem a good idea to you. Remember, the formula was for the coefficients was 1 over 2 pi I contour integral around C of dz 1 over z minus a, the function, times z minus the point you are taking the integral about or expanding about to the nth power. It's actually going to be n plus 1. Apologies for that. So if you like sort of club these together, dz and 1 over z minus a to the n plus second. Well, what's contour C? Some contour going in the anti-clockwise direction that's centered around the expansion point g equals a, which also happens to be a singularity point. So that's the interesting thing about finding if this or checking if this is a pole or not. You have to expand it around the singularity point. Okay, so what we can do is we can break this into cases. Cn is going to be 0 when n is going to be less than -1, because if you see, if the denominator has a negative power, it will go in the numerator, which means this integrand will no longer have any singularities or any like regions where like the function is blowing up. So Cauchy-Gursa will dominate and make the entire integral go to 0. It's going to be 1 when n is equal to -1, because when that happens we have z minus a to the first power in the denominator, and then we can just use a Cauchy integral formula. Well, for Cn, for n is greater than -1, Cn is actually going to be 1 over n factorial, nth derivative of the Cauchy integral formula. It's 1 over z minus a evaluated z is equal to a. But if you kind of calculate this out, it's going to diverge, because let me just write it this way. It's going to look like this. You can also see that it diverges using the fact of the geometric series way of finding these coefficients. You factor the stuff out, the condition of convergence is not satisfied for any of this. So this guy sort of doesn't exist really. You can't really find these greater than -1 terms. So 0 and all the other positive terms are basically not there, which means all of this is just gone away. Well, all the other terms which are less than -1, so -2 till negative infinity, they're all 0. So all that's left is 1 times z minus a to the -1 power, which is z minus a in the denominator. So by hook or by crook, because there's no other like higher negative power in magnitude, so according to this definition, the most negative term in the Laurent series has a power of -1. I may not have framed this properly. All I want to say is, if the magnitude of the power of this polynomial part in the denominator is say m, then that's the order of the poles. You want to find the highest in magnitude power of these negative sort of polynomial terms. So in this case we only have one negative power, which is -1 in the Laurent expansion, which means that f of z equals 1 over z minus a is a pole of order 1. In other words, it's a simple pole. I think I might have confused you slightly by my framing of words, but I will try to prove this point with another example. So f of z, assuming that is 1 over z minus a to the third power. Well, you can do the exact same thing that we did here. You're going to get a slightly different condition. I think you're going to get for less than -3 and then equal to -3 and greater than -3, and you're going to get similar constants. So 0 for less than -3, 1 for equal to -3, and well, sort of divergence for greater than -3. When you repeat all of these steps, and then you realize that in this entire expansion you just have 1 over z minus a to the third power as just the first term. For the poles, you don't really count the positive power terms. You only look at the negative powers, and you also look at which negative power is highest in magnitude. So here you have like the highest negative power will be 3. If assuming the highest negative power in the Laurent series expansion about z is equal to a were 4, then it would be a pole of order 4. But since 3 is only what remains after doing this entire case-wise sort of approach, you can conclude that it's a pole of order 3. Again, these were simple cases because you see that z minus a to cubed, 1 over z minus a cubed is basically sort of like exactly like one of those terms in the Laurent series expansion. So other terms just have to cancel out. These were easy. Others might not be easy. If you have some other polynomial in the denominator that does not necessarily factor out to z minus a cubed, then you might have to do a little more work. So the way I like to think about poles is that is the simplest way to make a function blow up at the singularity point, say z is equal to a. And the most easiest way the simplest way of doing that is basically taking that factor in the denominator, which was basically the first example I showed you. That's why it's called a simple pole, because the simplest way of doing it. Then you can also take higher powers of this simple case, which gives you, if you raise it to power m, this is an m order pole. In this previous case we had m is equal to 3. So these are simple ways of doing it. There are other complicated ways of doing it, taking weird functions like exponentials -1 in the denominator and stuff like that. But again, this may or may not be a pole, or even stuff like sine z over z is not really a simple pole, and I'll cover this briefly in a few minutes. But you can have something crazy or something that's at least comparable, or something that can be replaced entirely by some polynomial part, and then you basically reduce it down to one of these cases of finding a way to conveniently blow it up. I'm gonna do these examples, so don't worry. Okay, one important example: sine z over z. Okay, the thing is, the denominator blows up at z equals to 0, and you take sine of 0, it also is 0. So we have a 0 over 0 case. You may consider doing L'Hopital's rule, but whatever. I just want to show it in a different way. The Laurent series for a sine can basically be sort of extended from the real valued sine. That's a really useful property of trigonometric functions of complex angles. where z is a complex number. Well, sine z over z is going to be sum from n equals 0 to infinity, -1 to the nth power, z to the 2n divided by 2n plus 1 factorial. You write some terms out, 1 minus z squared over 3 factorial plus z to the 4th over 5 factorial, so forth. You notice when you take the limit, so as I said, taking the limit as z goes to 0 on both sides, for this guy and for this guy, you notice that you just end up with 1 because 1 is not affected by the limit. Everything else will have a higher and higher power of z, which eventually, on taking the limit becomes 0. So although the entire thing has, or is sort of close to blowing up because we have a 0 in the denominator, z is equal to 0 is not a pole. It's not actually even a singularity, because the function does not blow up. I mean, the function does not exist. That's a precise way of saying it. The function does not exist, but the limit does. So, and it violates the definition of a singularity because we wanted f of z in the limit that z goes to a to blow up to positive or negative infinity, which does not happen here. So z equals 0 is not a pole, and you need to be careful. So whenever you see a 0 in like a z or like a simple polynomial term in the denominator, it's not necessary that it is a pole. It's not even necessary that it is a singularity point. Stuff like e to the z minus 1 over z is also, there is no singularity at z is equal to 0. A fact that is actually pretty usefully demonstrated using L'Hopital rule, but you may not erroneously consider that a priori, looking at it superficially. But honestly, the reason why we should even care about poles in the first place, or even categorize them separately in terms of classification of singularities, is because poles are removable singularities. What I mean by that is, if you've identified that a function has a m order pole, you can remove it by multiplying z minus a to the order of the pole. You can use it to remove a pole, but you can also use this to detect the order of the pole. And the advantage of this is you can skip the entire Laurent series drama. I can maybe briefly give you a demonstration, but let me first mathematically write what this means. So if you have limit as z goes to a, f of z, and this goes to negative or positive infinity, we know for sure z equals a is a singularity point. Fair enough, but we don't know what kind of singularity it is. Assuming limit z goes to a, f of z, z minus a to the m, this entire thing is finite for the smallest m possible, then f of z has, again, m should be finite and it should be an integer. I mean, the logic for this is clear. Like, if f of z has a pole of order m, the function would be comparable to some basic function on top over z minus a to the m. So if you multiply by z minus a to the m, this cancels out, and then you take the limit, then g of a will be something finite because you've removed like the part that was even causing the problem, the function entirely to blow up. So this is like the logic behind this. Again, since we want to find the smallest m, we should start with case 0. So when m is 0, which is basically the definition of a singularity, and of course it's going to diverge because we first want to check if it's a singularity or not, otherwise it can be misleading, like sine of z over z. Then you check for, then you multiply by z minus 8 to the first, take the limit. If that is finite, then you can conclude it's a pole of order 1. If it's not, if it's diverging to infinity, then you need to multiply f of z with z minus a to the second power, take the limit, and then check again, and then keep increasing the power of this multiplying factor until you reach a point where it's no longer, where the limit is finite. So what I can do is I can give you a few examples to just make it clear how this mechanism works. Okay, example 1, f of z is z over cosine of z minus 1. Well, what we can do is, if you sort of try to check for what points the denominator is sort of going to 0, because those points are clues to whether or points to check for singularities. They aren't a guarantee, they're just you can check. Well, if you notice z equal to 0, cosine of 0 is 1, 1 minus 1 is 0, and we have a 0 on top. We are sort of like restricting our domain, so things like 2 pi and stuff like that, we won't really talk about them here. Okay, so what we can do is we can like check whether it's a singularity or not. So take the limit as z goes to 0 of the function f of z, which is limit as z goes to 0, z over cosine z minus 1. Now one way to do this is use L'Hopital because it's a 0 by 0 situation. What I choose to do instead is something interesting. Notice the identity 1 minus cosine of z is 2 sine squared of z by 2. This is sort of one of the cosine half angle formulas. Well, I'm going to use that in the denominator, so I have limit z goes to 0. I'll have a negative because I'm flipping the sort of orientation. So I'll have 2 sine squared z by 2. And also notice the identity sine of h over h in the limit h goes to 0 is 1. Well, this is also true for the square of this guy. So we can use these identities. Notice we have a sine squared. What we can also do is, in the limit that h goes to 0, sine squared h is equal to limit as h goes to 0, h squared. This is actually a bad way of doing math, like bad notation, unhealthy. But I'm just saying that it's sine, just the way sine x can be approximated as x for small x. That's exactly the same way of doing it. Sine squared x can be approximated as x squared for small x. So that's exactly what I'm doing here, and this is valid even mathematically because we are taking the limit anyways. We have z over 2 divided by, instead of sine squared z over 2, we can have z over 2 the entire thing squared, which is basically z squared over 4. Notice we have negative 2, limit as z goes to 0 of 1 over z. This clearly diverges to negative infinity, taking of course the positive direction first into consideration. So it is a singularity. Well, we know that. Great, good job. What can we check? Let's find the order. Now for the order, as I said, check for z minus 0 times f of z. Take the limit as z goes to 0. Check whether this is finite or whether it's diverging. So if we do that, limit z goes to 0, z times f of z, which is basically limit as z goes to 0, z times z squared over cosine z minus 1. We have negative limit z goes to 0, z squared over 2 sine squared z by 2, again using the thing I used before, and again repeating sort of the same process as before. I have z squared over 2 and z squared over 4. Luckily this cancels out, all the z cancels out, and we have negative 2. So it is finite, which means f of z has pole of order, well, you said it, 1, because we checked it with 1, so that must be the order of the pole at z equals 0. Good for us. Fine, nice. Okay, moving on. Say f of z is z over cosine z minus 1 entire thing cubed. Well, we can check again the shady point z equals 0, again restricted domain. Check for the limit to determine whether this is even a singularity point or not. So we have z over cosine z minus 1 cubed. This is a similar example to the one before. We can use this like similar properties in the denominator. Instead of cosine z minus 1, we have negative 2 sine squared z by 2. So 2 cubed is 8 because we have a cube outside. Sine squared cubed is sine to the 6th z by 2. And now remember this entire thing we did where sine squared z by 2 could be replaced by z by 2 squared in the limit that z went to 0. Well, we can do the same thing for a 6th power 2 because that's basically like multiplying 1 anyways. So we have z over 8 divided by, well, z to the 6th divided by 2 to the 6th power, which will be 64. You simplify with negative 8 limit z goes to 0, 1 over z to the 5th, which diverges to negative infinity. So even this is not even a pole of order 1, so we have to try for, I'm sorry, we weren't even checking for a pole of order 1. This is to confirm that it is a singularity. And now let's check for pole of order 1. So check for z times f of z, which happens to be, I'm gonna separate these with pointers so that we don't confuse ourselves. Z squared over cosine z minus 1 cubed, repeating all of the steps until we reach this guy. z to the z squared over 8 divided by z to the 6th over 64, which will give you a factor of negative 8 times limit z goes to 0 1 over z to the 4th, which will again diverge. So it's not a pole of order 1, it's something higher. So if you keep doing this for, say, check for order 2, this will again diverge. It's not order 2, it's not order 3 either. You keep doing this and you might have sort of noticed what order we need this thing to be. Since we have a 6th power, we need the top to be a 6th power. Right now we just have z, so we need z to the we need to multiply by z to the 5th, which means we need to check for limit z equal to 0 z to the 5th f of z, which turns out to be limit z goes to 0 z to the 6th over cosine z minus 1 cubed. Repeat those steps as before. Z to the 6th over 64, and you get negative 8. So you see it for this guy it's finite. For z to the 5th it's finite, which means we have a pole of order 5 at z is equal to 0. So you see these things can get crazy. We just need to keep checking. Advantages for crazy functions like these, where we have some weird cosine trigonometric junk minus some constant raised, entire thing raised to the 3rd power. It would have been really hard to do a Laurent series expansion using the contour integral definition. So that's where this idea of a pole, or this pole on the basis of removability, or multiplying by a certain factor to get rid of it, and then just doing an exercise in limits, or even L'Hopital's rule if you don't want to do this trigonometric sort of sine kind of approximation that I did here. But you see, this is a really nice method. Okay, you remember we classified poles as removable singularities. Well, the reason for classifying these as removables were that there are non-removable ones, or you can't use the method. You cannot use the method from the previous page. The method of like multiplying by this factor and then increasing the power, finding the smallest possible power. You can't use that. That's because there is no finite order for these guys. And what I mean by that is, if you the entire thing about a pole was that its Laurent series had like a smallest kind of had the smallest power for this z minus a factor, and then the positive power just went till infinity anyways, but it had a finite start point and end point was at infinity, if it even existed, because in the first two examples that we did very first, they didn't exist. Well, for these non-removable singularities, we have an infinite start point, which means that sort of m is sort of tending to infinity. M is not finite for non-removable singularities. And that's why we can't really use this method of z minus a to the m times f of z to check and then check whether this is finite or infinite, because we would also need to take the limit as m goes to infinity along with the limit that z goes to a. So this exercise is entirely pointless. What we can do is sort of write down the Taylor series for Laurent series for such things, because we don't really have a choice. This method of multiplication was really nice as long as they were removable, as long as there was a finite start point to our Laurent series, but now we don't, so we just have to go back to the roots. We can't escape the harsh reality. Poles made it seem like we could escape the harsh reality, but we can't really with these non-removable ones. Functions such as e raised to 1 over z, and if you write like the sort of Laurent expansion, 1 plus 1 over z plus 1 over z, entire thing squared times 1 over 2 factorial. I'm just using the Taylor series for e because we can basically sort of import it from the real world to the complex world, just like the trigonometric functions. But you see the power of z basically keeps increasing in the denominator. That's why I conclude that, you know, we don't really have a starting point if we were to write these terms in terms of a Laurent series, because the only non-negative power of z we have is 1. There are no positive powers. And the negative powers don't come to an end. So these non-removable singularities are what we call essential singularities. So there's really no escape from them. You just need to sort of visualize it. Usually there are functions which have 1 over z or some like reciprocal relationship in the argument, that instead of like increasing powers in the numerator, increase powers in the denominator. So you can even take sine of 1 over z, cosine of 1 over z, natural log of 1 plus 1 over z, but I won't really discuss natural logs. They're weird, messed up functions. But I think you get the idea. So you want the powers to increase in the denominator infinitely, no end to their increase. So these are essential singularities, which are sort of the antithesis of poles, because they actually force you to use the Laurent series. With poles you have a choice. So if you kind of, you know, see no end to your sort of removable process or like process of finding the order of the pole by multiplying, you see no end to that, which means you're most definitely dealing with an essential singularity. Most times you just have to use your like logic or your common sense, a little bit like I did for the cosine case, noticing the power in the denominator. The cosine z minus 1 was comparable to a z squared, or in the cubed case a z to the 6th case. Then I could smartly just take z to the 5th and then conclude it was a pole of order 5. With essential singularities, you know, there won't be such an intuition. Plus, I mean, what will you multiply this by anyways? It's gonna keep on, like, you can't, even like Laurent series or even like L'Hopital's rule is kind of hopeless, to be honest, for this guy. It's just indeterminate anyways. So I noticed the fact that we are conveniently out of time for this video, and again, it's not a good idea to start a new topic. I think that's it for this video. Stay tuned for more content. Keep home, keep doing math, and I don't know, just comment in the comment section if you have any more doubts. See you in the next videos. We can talk about residues in the future. So peace out till then.